Welcome back to part 2. Okay, so some of these I didn't give you the answers, so I might have to think off the top of my head. Um, the only problem with this question is this red light. Which one is likely to absorb let's just say the most energy? We changed the question so it's more realistic to what I would ask you. Which one is absorbing the most energy? B, yep, that's the greatest increase in energy. If you were in a different, focused, maybe Kevin wants to actually calculate the energy, he could calculate energy at energy 1, energy at energy level 2 or 3, and the difference, and calculate the specific wavelength. You can calculate all that, we just don't do that. What is a true statement about electromagnetic radiation? This is true, right? Wavelength is inversely proportional to frequency. As one increases, the other decreases. This is also true. The velocity of electromagnetic waves is constant. I'm not sure that this guy is a good teacher. That bothers me. I know that D is not true, C is not true, and A is not true, but he has 2 correct answers on there. The velocity of electromagnetic waves is the speed of light. The speed of light is a constant. Hey, Mr. Murphy, what about the speed of light in water or in air? Doesn't it slow down? No, it just bounces around a bunch, and so its pathway is longer. It would be like if, okay, so say that Arthur sprints down the hallway at full speed after school. You got that mental image? Is there anybody in his way? No. And then it's between second and third period, and Arthur sprints down the hallway with people in his way. But it's Arthur. And he's not slowing down for anybody. Guy, girl, 9th grader, teacher, laptop cart. And he is just hitting things and bouncing off of them and then leaving at full speed. The collision occurs. You got the sound effect? Good. And then he flies off at full speed without slowing down. So it's like boom, 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 boom. Is the pathway now straight? No. So the distance is longer as he travels down the hallway because there's a bunch of zigzags and collisions occurring. But he's constantly moving at Arthur's max speed, destroying people and things left and right, which would be awesome. This is what the light is doing. It leaves outer space where it's pretty much an empty vacuum at 300 million meters per second. And then it enters air and it slows down. No, it just is bouncing off of crap. And it goes from 300 million meters per second to 299 million meters per second. In water, it slows down a little bit more because there's more crap bouncing it off. It's bouncing off of. But it's not actually slowing down. There's just things getting in its way. Which element is characterized by 5 valence, 4th energy level? It's got to be on the 4th energy level. That would be arsenic. Arsenic has 5. We got a little periodic table. There we go. And it was like 1, 2, 3, 4, 5, 6, 7, 8. You could pretty much just count across the periodic table and figure out how much valence electrons they had. Arsenic is in the 5th, and it's in the 4th. There you go. Why does it count that way? Because on the periodic table, pointing, people can't see the pointing. These are our 1s's, our S1s, our S2s, and then the entire D's are all lower energy, so they don't get counted towards the valence. So it'd be like S1, S2, then we get a P1, which kicks the valence up to 3, a P2, a P3, a P4, a P5, P6. Which element is characterized by ending in 5D4? I think it's tungsten. Am I right? Score. Again, this teacher is not a good teacher. That's actually one of the few exceptions on the periodic table, and he chose poorly. You don't have to know the exceptions, though. Tungsten actually is a cheater. It takes an electron from the S's and shifts things around. We don't learn the exceptions. It just irritates me when people ask questions about the exceptions. 5P2? That's my guess. Am I right? No? Am I off by 1? 6P2? Ugh. was trying not to look at the periodic table. Lead is 6p2 at the end. What would be the electron configuration of the boron family? They are s2p1s. Right? Everyone in the boron family is an s2p1, s2p1, s2p1. Hey, what about the Ds? They'd be, when you get to the Ds, they'd be ns2, n minus 1, d10, np1, I guess. Because any of the d orbitals would be a lesser energy level. So therefore, they aren't actually in the valence. They'd be n minus 1. So. How many electrons are possible for one d orbital? This is a trick question. Don't be tricked by it. 2 is the right answer. What the flip? It says orbital. One orbital, not the whole sublevel. If the question had been how many electrons are in the d sublevel with the odd emphasis there, then it would have been 10, right? Orbitals can hold 2. It doesn't matter if it's an s, p, d, or f orbital. It can hold 2. The sublevels are multiple orbitals. How many possible orientations are there for the Ds? There are 5, right? You could have one. There's the 5 orbitals. We were talking about the different shapes of the orbitals a bit ago. And there's 5 orbitals where they have different shapes. We don't do this. Here, so I'm just going to draw off that. Number 11. This one really threw my other class off. The answer is C. Why is it C? I don't like that. I don't understand what the heck is going on. First of all, let's pick an element. You, pick an element. Phosphorus, okay? And then we're going to take an electron off of phosphorus, and now it's phosphorus plus 1, and that electron has been removed. We're taking an electron off of phosphorus. Ionization energy is the energy to remove an electron. And so here's the before and the after. The electron's been removed from the phosphorus. So C is a representation of ionization energy. Which one would be a representation of of affinity, electron affinity? Electron affinity, again, is when the electron is added, it gets happy, like if you give someone a new pen and they're really excited about the new pen. Which one of these represents an electron gaining? A, right. So we have the normal element gaining electron, and now it has a charge on it. So that would be affinity. E is just wrong, right? You have the normal element losing an electron, and now it has a negative charge. That doesn't work. That's just wrong. What is B? Can't hear you. No, not covalent bond. It's an ion gaining its electron back, isn't it? It's an ion gaining its electron back. And D is also not a thing. The charges don't add upright. But, all right. Which group has the greatest electron affinity? Which group releases the most energy when it gains an electron? Do the noble gases? Do they gain electrons easily? No. Halogens. Yes, the captain gets it right. Yeah, the halogens only need one electron to fill up their stable octet, and they release a lot of energy when they gain that electron. They're like, yay, we made it to 8. They have a little party. All the electrons dance and shimmy. None of that was true. Okay, this looks like it would probably be a positive 3 charge. Why would it be a positive 3 charge? There's 3 valence electrons. It could probably give off 3 valence electrons. Let's do a different one. Let's say we had What charge would something like that probably take? If you can't, like, if you're really stuck, just pick an element that would be that. It would be S2P4. What's the charge of oxygen? That's probably the charge of an element with that configuration. It's 2 electrons away from being a noble gas. This one was 3 electrons away from losing them all and being like a noble gas. So they transition into the noble gas states most likely. We didn't do absorption spectrum. There are some pictures back there, but probably the best example is just look around the room. You see shirts of various colors, and this is kind of an example of absorption. You got the purple and the orange on that one. That's an interesting combination. What colors is the purple part of his shirt absorbing? If you didn't hear that, they said all of them except for purple. Yeah, right? Does that make sense? Well, we see the same thing with elements. If you shine in a complete wavelength of light, like all the colors of the rainbow at an element, the electrons can only make certain transitions because they can't go to 2.5 or they can't go to 1.4. They can only go from one value to another value, and so they only absorb light that equates to those transitions. Good? Just like they only release light that equates to those transitions. So absorption spectrum are kind of the inverse of emission spectrums. There it is. Just had to read all the answers to find them. And behind the guy in the tie-dye shirt, you could see the absorption spectrum for chlorophylls, the second one down. So you got red, dark band, dark band, dark band, lots of green, lots of purple, lots of blue, right? And so leaves absorb red light, they absorb yellow light, they don't absorb much green light, which is why leaves typically appear to be green to us. The chlorophyll appears to be green because it absorbs those other spectrums. Why are the leaves changing outside? Not just because fall is beautiful, but the sun's at a different angle, and the wavelengths of light that are reaching us start to change, and the leaves, as they die and start to get pushed off, they don't fall off, they get pushed off the tree. As the leaves before they get pushed off the tree, the chemical composition changes so they can absorb different wavelengths of light that they don't normally absorb, because the angle of the light coming and the wavelengths of light we get from the sun are different. Fall should be called push, right? If you zoom in at the cellular level, you could see that the cells are slowly separating and thinning out the connection, and then eventually they just go poof, and they push it off. Right? It would be the equivalent of you deciding to get rid of a finger slowly, and the finger just slowly gets thinner at the joint, and then one day just drops off. And you're like, whew, can't wait till the spring when the finger grows back. They thought that was funny. It's kind of weird. I don't know. Which off-ball diagram's incorrect? I don't know. Which one's incorrect? You guys help me out here. A is incorrect. Oh, yeah, because the two P's are done wrong, aren't they? Right. Okay. Which orbital fills after the 5s? That would be the 4D. Did you know that it goes 6s, 4f, though? Did you know after the 6s is when you hit the f's? That's when the f's, yeah. And if you can kind of see the gap on most periodic tables, because 56, 57, 72. There's a big chunk there where the f's fit in. We don't ever hang out in the f area, though, because there's so many exceptions, all the questions would be false. They're like, this wouldn't be the right answer. Which one is true about one photon? I honestly am struggling here. Just a second. And so that answers that. Okay. Now, this is much more of a physics question and less of a chemistry question. Is there an overlap? Yes, there's an overlap. They definitely handle wavelengths of light better than we do. We like to look at the pretty colors and tell you what element it is. That's what we like to do with wavelengths of light. They like to find black holes and stuff. I don't know. Which of these contains an isoelectron? Isoelectronic means that they have the same number of electrons afterwards. So which one of those has the same number of electrons? Oxygen and aluminum. Oxygen -2 would be 10. Aluminum +3 would be 10. So they're isoelectronic. They both have reduced or gained their electrons to look like neon. Yeah, okay. Good? Which is false about atomic emission spectrum. I just bit my tongue. I gotta read all these. Too many. It's not that they're absorbing white light, it's that the white light contains all of the colors mixed together. If you mix green, blue, and red together, and I mean if you have a red flashlight, a blue flashlight, and a green flashlight, and you shine them all on the same spot, the wall looks white. All right, now the wall has to be white to start off with. I guess I should have started with that. If you have white paper on the wall and you shine a blue flashlight, what color is the paper? Shine a green flashlight, it's green, right? If you shine a green, blue, and red all at the same paper, it's now white. They mix together, and our eye interprets that color as white. Always keep in mind that it's really how your eye interprets the color. It's not actually what's going on there. We don't. That's really the hardest thing to understand. And I think we talked about how your eye just remembers the color after a second. You see a purple shirt, the cones and rods see the purple only for like a fraction of a second, and then they just remember it was purple because they get overloaded by the light. And they go, don't forget that was purple. It's just a weird thing that occurs in our brains. What is this one? Is it bromine and potassium? No, not potassium +1. That's not it, because it's not the potassium +1. It's not this one. It's not this one. Wait, is it that one? Rubidium. Oh. This is hard to do. Zirconium. Where's zirconium? No, no. Is it B? Yttrium and selenium? You don't get to say yttrium enough. Yttrium +3 and selenium -2. Someone tried to tell me yesterday that was vanadium. She was like, that's how you spell it? That's how I'm saying it. Vanadium. I was like, all right. Aluminum. First 3 ionization energies are pretty low. The fourth one's very high because the fourth one's in the core, right? Skipping 23. What was 23? Let me just come and look at this paper over here. I don't want to get too far away from my Bluetooth connection. Increasing atomic radii. Ooh, that one's tough. I think sulfur's the smallest, so it's either A or E. Where's titanium? Why can't I find titanium? Oh, there we go. Is it E? Yeah, E. E is the right answer, yeah. Because as you go across, they get smaller, right? As you go up, they go smaller. Because as you get across, the effective nuclear charge is increasing, which pulls the valence shell in. So titanium would be bigger than zinc, which would be bigger than selenium. But as we go up, we just decrease the number of energy levels, so it definitely got smaller. So the one that has sulfur, selenium, zinc, titanium. 24, put these in order of decreasing first ionization energy. Which one would be the easiest to take from? Which of these elements would be the easiest to take an electron from? Cesium would be the easiest. So cesium or cesium. We've just eliminated these two. Cesium is an alkali metal. It is the largest of the elements there, so it's got the most electron shielding, so its valence would be the easiest. Magnesium would be the second easiest. So now it's either A or D, or because magnesium is an alkali metal. And then is it argon or chlorine? Chlorine would be slightly easier than argon, so the answer is D. So you just kind of slowly eliminate things and work your way across. All right? Put these in order of increasing electron affinity. This one's dumb. Electron affinity is really hard to predict. No. The only thing you can really predict with electron affinity is like the halogens and the oxygen family have very high electron affinity. The others are all over the place. We looked at that pattern. It was like, in the notes were like high points and then a bunch of random low points and high points. And the only thing you really see in the pattern is that the halogens and the oxygen family are pretty high. I don't know. I would actually have to look at the data. Yeah, I would have to spend like hours on that one. Because I would be like, well, that one's a D4, so it's halfway full in the D orbital, and it'd be filling the fifth one. That could be good. You know, it'd be a lot of like really slow motion logic, or that one's all three half filled, and the fourth one would be filling up a half, and that's a bad thing. So good. It's not easy to predict that. So. Explain which of the following principles of atomic structure bonding. Oh, that's true. This would be smaller than that. Oh, explain each of the following. This is a free response question, isn't it? Sorry. I was like, well, I thought it was a true false. So why would sulfur be smaller than selenium? Sulfur would have a higher effective nuclear charge. Strontium would have a higher effective nuclear charge. Selenium, they have the same identical shielding at this point. Strontium plus 2, selenium minus 2, both have 36 electrons. So they're both 1s2, blah, 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 4p6. They're identical. But strontium plus 2 has 4 more protons, and therefore a higher effective nuclear charge. Ionic radius of nitrogen minus 3 is larger than the ionic radius of oxygen. That would also be explained by the effective nuclear charge. Both of them, again, would have the same number of electrons. They both had 10. But nitrogen has fewer protons, so it's a larger radius. Because a lower effective nuclear charge than oxygen minus 2. Calcium atom is larger than a zinc atom. They're both in the fourth period. So if they're both in the fourth period, what is not important? You have 50-50 choice. Effective nuclear charge or shielding effect. Shielding effect is not important because they have the same amount of shielding. They're both shielded by the 1s, the 2s, the 2p, the 3s, the 3p. The zinc atom has more protons, so it has a greater effective nuclear charge. Boron has a lower first ionization energy than beryllium. Really? I heard that noise. I heard someone go, tch. I'm going to think. I don't have an explanation for that. For you at home, I brought up the chart. We have the 1s, and we have the S1 and an S2, and a P1, and I'm not quite sure why, and I don't have an explanation, and I hate not having an explanation. but it's not following it right there. That's my issue, is that for a second it's not following it. You see the same thing here. This is like P1, P2, P3, P4, P1, and it's almost like when you start the P's, there's an energy drop. It's easier to remove from the P1. I think I remember something about like a full orbital is harder to steal from than a half full orbital or something like that, but I don't remember. We shoot for the general trend. As you go across the period, you see an increase, not for like comparing these two elements specifically. So, don't like not knowing exactly what to say. Values of the first ionization energies for magnesium and argon are some, and these terms configuration explain why the value of the first and second ionization is significantly lower than the third. So these first two for magnesium are the valence electrons. This one is a core electron for magnesium. Magnesium is usually a positive 2 because it's 3s2 at its valence shell. The third one would be a core electron. Whereas with argon, the third one's just the third one. It's still in the same p orbital. Argon is 3s2, 3p6. So these 3 electrons are coming from that p6. So they're not drastically different energy values. When would argon have its big jump if you were stealing electrons? How many electrons would you have to steal from argon before you saw a gigantic leap in ionization energy? You'd have to remove all 8 of its valence electrons. Because then after you remove those 8 valence electrons, you're then dipping into the core, the closer energy level. And the core electrons have less shielding on them. This one that's taken here for magnesium isn't shielded by as much. So it's harder to take. Element Q. It looks like the big leap is right after that first electron, doesn't it? So that means to me it's probably an alkali metal. You take the first one off with ease. The second one is 10 times greater. That's a huge jump. That's probably an alkali metal. That's me. Yes. This is ionization energy 1, first electron, second electron, third electron being taken. You can't get to the third electron unless you've taken the first 2. So this would be magnesium plus 1, magnesium plus 2, magnesium plus 3, etc. That's a good question. Is this the last page? Because a lot of this is outside of our realm. Explain what the difference between emission and spectrum. We expect to see we expect to see electrons move from one energy level to the other energy level and back again. There are specific energy levels because they can't move at anything but specific paths based off of the wavelengths of light, the wavelengths of the electrons. There are, of course, all sorts of wavelengths of light you can't see. Name a wavelength of light you can't see. Ultraviolet, X-ray, camel, that's not a wavelength of light. Gamma, is that what you said? Gamma, yeah. Microwave, what? Infrared. Some animals can see infrared, just not these animals, the humans. So maybe we'll have to add that to our genetic code by force. Really weird. So there are lots of different line spectra for elements. When you look at like the line spectra that we have on the wall over there, you're looking at just a pattern for that element. But there's also a UV spectrum and a gamma spectrum that's identical, similar. And we've talked about the different properties of metals and nonmetals so much I'm not going into that. Okay.